Hello, this is part B of the Chapter 5 lesson. Part A, we talked about the basic idea of probability and how to calculate probabilities in very simple examples. In this part, we're going to look at conditional probabilities, how to calculate them, and what do they mean. So let's look back at this same population of children, where again we had 5,290 children. Some were boys, some were girls, and then they were ages 5 through 10. So suppose we randomly select a child, and suppose that we select a girl, but we don't know her age. We might ask a question, or we might want to know the probability that the child is 9 years old. So we're going to denote this probability 9 years old given that the child is a girl. So the probability that the child is 9 years old given that the child is a girl. This is what we call a conditional probability. So it's the probability of something conditioned on the fact that something has already happened. We know the child is a girl. We want to know a probability of something more about that girl. Okay. So this again is the probability that we want to know. So we know that we're dealing with girls only, so we're not dealing with the 5,290 people in general in our population. We're only dealing with these 2,730 girls. So when we calculate this probability, that number 2730 is going to become our denominator. Now the numerator is the number of children in that set of girls that are 9 years old, which is this number right here, 461. So this is the number of 9-year-olds who are girls divided by the number of girls. We do that arithmetic and we get 0.169. Now let's look at another conditional probability. Let's suppose that we select a child who is 6 years old and we want to know the probability that the child is a boy. Now you may ask yourselves, well, how would we know the age without knowing the gender? Well, this is just an academic example, so don't worry about that. But conditional probability that the child is a boy given that the child is 6 years old. So given that we know the child is 6 years old, that means we're dealing with really only these 892 students that are 6 years old. So that number is going to become our denominator. And now the numerator is going to be the number of children who are 6 years old and a boy, which is 379. So divide those two numbers and we get our probability 0.4225. So to summarize what's going on here, to calculate these conditional probabilities, the denominator comes from the second part of the probability, and the numerator comes from kind of a combination of the first part and the second part. Okay. So let's talk about what do these probabilities mean. So our first probability, 9 years old given that it's a girl, is 0.169, means that about 16.9% of all girls are 9 years old. Or stated another way, the proportion of girls who are 9 years old is 0.169. Remember, proportion is just the decimal equivalent of a percentage. Our second conditional probability, probability that's a boy given that it's 6 years old, is 0.4255. Means that if about 42.55% of all 6-year-olds are boys. Or stated in terms of proportions, the proportions of 6-year-olds who are boys is 0.4225. Now let's look at, this is example 5.2 from the book, which gives results of from a PSA test and whether or not these guys develop prostate cancer. And so what we do here is we've got a population of 120 men. We give each man this prostate test or PSA test, and they get one of 3 scores, either a low, a moderate, or high. So 64 guys had a low score, 41 got a moderate, so on and so forth. And then we also look at whether they develop prostate cancer in the future or not. So 28 of them did develop cancer, 92 of them did not. This number here says that 3 of the guys who had a low PSA developed cancer. This number here says, for instance, that 28 of the guys developed moderate prostate cancer and or had a moderate level of PSA, but did not develop prostate cancer. So suppose we randomly select a guy from this population, and let's suppose that this guy had a low PSA score, and we might want to know what's the probability that he has cancer, or that he did develop cancer. And so we would denote this probability of cancer, given that he had a low PSA. So we already know that he had a low PSA. We want to know the probability that he has cancer. Well, we can calculate this probability in the same way as in the previous example. The denominator is the number of guys who had a low PSA, which is 64. The numerator is going to be the number of guys who had a low PSA and prostate cancer. So 3 divided by 64, that arithmetic is 0.047. We might calculate some other probabilities, other conditional probabilities in the same basic way. Suppose that the guy had a high PSA. We want to know the probability that he has cancer. And so we have the denominator is the number of guys who had a high PSA. The numerator is the number of those guys who developed prostate cancer. 12 over 15 is 0.8. Another one, suppose that he has a low PSA. What's the probability that he has cancer? So the denominator is the number of guys who have cancer, and the numerator is the number of those guys who have a low PSA. So 3 divided by 28, which is 0.107. Now, results from tests like this can be broken up into kind of 4 different categories, or 4 different types of results. The first type is what we call a true positive, and that's where we get a positive test result and we actually have the disease. A true negative is where we get a negative test result and we do not have the disease. A false positive is where we get a positive result but do not have the disease. A false negative is where we get a negative test result but actually do have the disease. Now, medical tests are not perfect, and so that's why we can get false positives and false negatives. So we need to take those into account when analyzing the results from tests. Okay. Now, associated with these 4 different categories are some definitions. The first one is called sensitivity, and that's described as the true positive fraction. In terms of conditional probabilities, it's the probability of testing positive given that a patient has the disease. Related to this is the specificity, which is also described as the true negative fraction. That's in terms of conditional probabilities, the probability of testing negative given that you do not have the disease. The false positive fraction is the probability of testing positive given that you are disease-free. The false negative fraction is the probability of testing negative given that you have the disease. So let's look at calculating these different numbers for this particular example. This is example 5.4 from the textbook, which gives the results of a screening test for Down syndrome in a population of 4,810 women. So each one of these women was given the screening test. 360 of them had a positive result. 445 of them had a negative result. Out of those, 10 women had a child that was affected with Down syndrome, and 4,800 of them did not have a child with Down syndrome. This says that 9 of those who had a positive screening had an effective a baby, and so on and so forth. Okay. So, for instance, to calculate the sensitivity of this particular screening test, that is by definition the probability of testing positive given that you have the disease. So in this case, the disease is an affected fetus. And so what we need to do here is take the total number of defective fetuses, which is 10, and divide that by the number of those mothers who tested positive, which is 9. So we get a sensitivity of 0.9. Now a specificity, that's not pronounced correctly, I apologize, but it's the best I can do, sorry. That's by definition the probability of testing negative given that the person is disease-free. And so we're going to take the denominator as the number who are disease-free, which is the 4,800. The numerator is the number of those mothers who got a negative test, which is the 4,449. Divide that, we get 0.927. False negative fraction is the probability of testing negative given that they have the disease. So the denominator is the number who have the disease. The numerator is the number of those mothers who got a negative result, which is 1. So 1 divided by 10 is 0.1. The false positive fraction is, by definition, the probability of testing positive given that we are disease-free. So the denominator is the number who are disease-free, 4,800. The numerator is the number of those who got a positive result. So 351 divided by 4,800, that's 0.073.